The first speaker of today's sessions is Professor Samuel Fourn, and he will continue with his talks yesterday.
Thank you. So, hello everyone. Today, as promised, I will explain the classical method of Chabauty. So, you can take it as the title of the talk. I'll give a few last results about what are the objects we need to study, and then we can prove the main theorem and see a bit more about variance and interesting cases for this. First off, I think yesterday I promised you some more details about what the logarithm exactly is. Well, I will, but first I will say just a little bit with what we know on the case of an abelian variety. So I'll just say a bit more now and more afterwards. So let's say Q abelian variety. Then I define the log, and let's call it log subscript A when it's ambiguous, but well, if you're looking at things in A, it will be obvious. So it goes from A of QP to the tangent space at 0 of A. Oh, yeah. Is it working? Yeah. It goes from A of QP to the tangent space at 0 of A, which is isomorphic QP power D, if D is the dimension of A. All right. One way to think about it, as I said a bit yesterday, is if you know about Lie theory, so Lie groups for over R. Well, it's the same thing. For Lie groups over R, you have a log locally defined around the unit. There, you have on periodic numbers, you have a not so locally defined log sending you into the tangent space, and basically it's because the topology is a bit different. So we can extend the log to all the variety, and it's well defined, and it's additive. So log of a sum is sum of logs here. So it helps you understand a bit more about this in particular, and that's what I wanted to say. If you don't really yet have an idea of what this looks like, I said it a bit, but log is additive. Locally analytic. The kernel is just the torsion points. Which is finite here. And the image is a subgroup of QP power D, like this, which is isomorphic to ZP power D. Here. I added in the notes some more details, at least in the case of Jacobians, about what exactly is the shape of this. So you see here you have a lattice inside the tangent space. We can be a bit more precise, but for now, let's just, now you have a bit of an idea of what it looks like. Okay. So as I said, I'll say a bit more of what I need, and the next, I think, 3 or 4 results, we'll be talking about the one forms. So the differential forms over the varieties I need, and they have a lot of nice properties. So I try to sum them up here. Again, so it's true for every base field. So I take an abelian variety, and I look at omega 1. I will often be a bit lazy and just write omega 1. But given the context, it will always be omega 1 A over K, the sheaf of scalar differential forms. One. Okay. So when I write omega 1 all the time, it will be this. And actually, it has a lot of very nice properties. First one is that it's a free OA module of rank D, again, D the dimension. Okay, so it's actually pretty simple to study. It's not a weird sheaf having weird sections, etc. It's a free of the rank I imagine. So this is a good point, and has as a consequence this fact, for example, that I could take the global sections of the sheaf and restrict them because it's a one form. So it defines linear forms on every point. Okay, and there on the abelian variety, I have an obvious point, which is 0. So I'll look at what happens when I restrict to 0. And so it goes to the cotangent space. And the cotangent space is exactly the dual of the tangent space. Okay, so if I take omega like this, I restrict to 0. This defines a good old linear form on the tangent space, right? Well, you might think, in general, we lose information by doing this. Not in this case. In here, it's all the same. It's an isomorphism. Okay. And furthermore, I can rebuild from there a global form here. And it's pretty obvious once I'm able to prove that the one forms that are globally defined have to be invariant by translation. So if I translate them by every point of A, I'm supposed to get the same form. So now, once you know what happens at 0, you should be able to know what happens everywhere. That's the idea. Oh, again, I don't have time to give any proof for this, but I gave different references in the lecture notes. And all regular global one forms are translation invariant. And also, well, if you think about one forms, you think about a differential operator. So there is for this sheaf, there is a canonical differential operator D. So I can ask what happens when I apply D to one forms here. It turns out they are all closed. So the differential operator vanishes on all these forms. So basically, we have the best we can hope for. Okay. But what I will do is that, well, of course, I will use one forms on abelian varieties, but at the end, I'm talking about a curve, right? So I want to understand what happens for the one forms for the curve. So why am I talking about this? Well, for the next reason. So if A is a Jacobian of C, and here I'm a bit loose with notation because it could work with any curve over a field K and any Jacobian without any problem. But it will work in particular for what we want to study. I take one forms on J, global ones, and I have a morphism from C to J. If you remember, I defined iota, maybe I could call it here, C to J, which to P associates the class of the divisor P minus B. I've chosen the base points. I could write I subscript B everywhere, but it will be a bit tedious. So let's just say I fixed it. And with this, I can pull back a one form here to get a one form here. And if regular global goes to regular global, so I get this pull back, and it turns out it's also an isomorphism. Okay. So now it means I can see any form omega, let's call it omega j here, as a form over C, which I could say is iota star omega j. All right. So in my perception now, it's almost more convenient to think about some sort of abstract space of one forms. Okay. And I can see them either on J or either on C, depending on my needs. All right. So I will call it omega C to say, I really want to think about it on C, and omega J when I say I really want to think about it on J. Okay. And that will be the main things we use. All right. Now, I said it yesterday as well. Ultimately, we want to have good equations, good power series. And for this, we want to have integral things. We don't want to have manipulate coefficients that could be too bad of elements in QP. So we need everything to make sense integrally. Well, we can do that integrally, but I will just say one of those for convenience. It's what happens. Oh yeah, sorry. Here I should say this now is also independent of B actually. But this is quite easy to see because if you try to change B, it will amount to translating the form here, and it's invariant. So because it's all invariant, it doesn't change. It doesn't depend on B. Yeah. So here we can do the same. For this can be defined over any scheme over any base. Well, I will do this for the model of a curve. So let's say C model of C over ZP. So it's defined over this ring, and when I look at only the generic fiber, I get back C. Now I can look at three different spaces of one forms. One forms over CZP here. One forms over the generic fiber, and I use QP just to have p-adic things. I could say the same over Z or Z, etc. But well, for us, we only study what happens p-adically, so this is the right information to go for. And finally, let's say smooth. Of course, it's not interesting. Here, I can also reduce mod P and see what happens. Okay. So first, you have obvious morphisms because this means one form of the whole if I do a drawing. So I have, this should be CZP. Here, CQP, which is also CQP, and here CFP. Okay, so generic fiber, special fiber, both smooth, so I'm allowed to draw something like this. I just restrict to either this fiber or this fiber. So this is well defined. Okay, and now what can I say a bit more precisely? Well, I know that this it's also isomorphic to H0 of JQP omega 1, and the latter is of dimension G. So this looks like QP power G. Well, now this is actually a lattice in here, so it injects as a lattice in those ones. All right, and finally, this reduces, and I can prove it's not so easy actually. Again, reference is in the lecture notes. I can prove that this reduction is exactly the same thing as tensoring by Z over PZ, ZP over P here. Thank you. So this is the same thing as tensoring by ZP over PZP. So tensor FP here. In particular, it's surjective. And so this looks like also, I knew this before, FP power G. All right. Yes. Yeah. Sorry, I should have said proper as well. Yeah. So the same thing as before, I have fixed a smooth proper model. Well, I didn't want to say that. So yeah, it's also the Nero model, but in the very easy case, yes, smooth proper. So everything works as I said yesterday as well. Yes, thanks. So to fix the ideas, basically you have a space that's a vector space over QP, inside which you have a lattice. So ZP power G looks like it, which reduces nicely to the space over FP you want to think about. Basically, that's it. And I could do exactly the same with the Jacobian and the models. So here, Nero model of the Jacobian with JZP, JQP, JFP, and it would all be isomorphic and all be compatible with this. Okay. So we want details. You have also living isomorphically to this here. 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 So here, let's say J is a Nero model. J over. So this is an abelian variety, smooth. No, I mean scheme over ZP, smooth. All right, so it makes sense to talk now about what is integral, and that's why I bothered with this definition. So, a form inside this space is then normalized integral. So if it comes from the integral lattice, so H0 CZP omega 1, and its reduction mod P, so that's for normalized. Reduction mod P is non-zero. Okay? And the obvious thing you can say is if you start with any form non-zero there, you can find the coefficients, you can multiply it to land inside this lattice. And to land, but not too much. You can make it so that you land inside there, but not being a multiple of P, so that you don't reduce to zero here. So basically what I'm saying is that it's exactly the same thing as when you are dealing with integers. You can multiply by a good coefficient so that you get in the right space you want. All right. So now I define the logarithm and one forms. I could do already a lot of things with this. But what I'm going to explain now is p-adic integration. Okay? So p-adic integration will be a way, and quite miraculous, to integrate one forms, closed one forms, from one point to the other. All right? Of course, the big problem with that, and I will explain more afterwards, is that the topology of QP is very bad. You basically have a bunch of disconnected things living. So on each thing you can try to integrate to define a disk, but there is no reason to expect that it could work over the whole space. And actually, that's what we'll manage to do anyway. So I'll first define what I will call the log as a function here. So first, the logarithm, I want to have a logarithm that does this. I want to satisfy two properties and one last, just to be sure. So first, I want it to be what I imagine when the power series converges. Okay? First, log of 1 minus x is minus the sum here of the xn plus 1 over n plus 1. And this is for all x of norm less than 1. So this is the usual power series. I'm fine. Now I also wanted to have the formula for the log. So log of xy is equal to log of x log of y for xy in qp star. Okay, I want it to satisfy the formula. That's a second good thing. And now, when I look at this, I try to figure out. I can actually easily. I can define functions like this, but I have many choices. And why do I have many choices? Because I haven't prescribed what should happen to logarithm of p, for example. We have many choices, but here we'll pick log of p is equal to 0. Okay. In some cases, there is a theory of periodic integration with this considered as an indeterminate, and then we'll do everything with this known. Let's fix it, and we don't really care. It's enough for us to have this assumption. And you can check that this is well defined and uniquely defined. Okay. Now this was just the log. Now I want to define analytic functions with this. So let's take x over qp. And I want it to be irreducible, but even over qp bar, if I just look at this, which means I call it geometrically integral, for those who know the vocabulary. Okay, just why do I do this? Because I want over qp at least, I want to define the function field of x, as in usual algebraic geometry. So here, I take a non-zero function over the function field of x. It's a rational function. I can evaluate it outside the poles, okay? And locally, it's also a power series. I can pretty easily think about it like this way. So now the goal is to think of everything I will say afterwards as a specific case of locally analytic function, okay? So you can really think of them as functions, just locally they look like power series. But remember, this is a bit too general in general, because you can have things like 0 on a disk and non-zero elsewhere. So it behaves badly, but if you want to convince yourself that this makes sense, you can think of it in this big space of locally analytic functions. Yeah. Yeah. No. Hey, you can really fix. I think maybe not for everyone. You have a freedom here. Yes, I think it's a good exercise to try to figure out where it comes from. Actually, you can. Well, I guess the main explanation, you start with anything here. You bring back to something of norm at most 1, and then try to get back inside the disk around 1. But you need to make a choice of how you size your evaluation, or your uniformizer. So here, log of f makes sense as a locally analytic function. Here, so it's really log composed with f. Locally analytic function defined by power series on, well, everything x minus the poles of f. Yeah, and poles on zeros. Okay, you don't take log of 0, you don't take log of infinity, but otherwise it's fine. And with this, I define a larger space than this, which is qpx log, which is the space generated or all in the middle of all analytic functions by these logs of here. Again, really I'm looking at locally analytic functions on open subsets of X. Because of course I cannot evaluate on pause, but it was already the case here. Okay, I have enlarged a bit the space. You'll be happy to know that this still satisfies the isolated zeros principle. So we don't have bad things happening with this. It's a result, okay? So at least we can hope to have some sort of a good behavior. I have a differential D that extends the usual differential. So it does go to this space. And I'll explain the notation afterwards. But what I want to focus on is what do you think should be the differential of log of f? And that's actually one of the main points of the definition. Yeah, df over f. So d log of f would be df over f. That's actually the only definition making sense, extending the usual one. And there, something very important happens. You start with something that's not inside QPX star, okay? It's a new function defined like this. When you take the differential, you get in this space, and this gets back inside QPX itself. Sorry, it gets into omega 1 of x. So it's a usual differential form divided by a usual rational function. So it's inside this space of rational one forms. So they are not global, they are just defined over an open subset like this. So you start here, you get back here. For this case of log f, of course, in the general, you might have some bad things happening, which is why you still need to extend your space. You might still get inside QPX log. But that's very important. It means, in other words, if you think about df over f itself, you have found a primitive, which is here. But you have needed to extend your space of functions. Okay? And the whole game, of which I will just give the conclusion, the whole game of what I explain afterwards is that you have managed to extend your space of functions, but not too much, so that the theory stays consistent and fine. But you can do these kind of things. You can find more primitives. Okay? And you have specific primitives. All right. Yeah, because I was a bit loose with notations here. If you want to look at this as functions on x of qp bar, for example, you will have a x splits, and then you don't have a integral t anymore. Okay, that's why. And you might want to think of this like function of qp bar. That's why. To be sure, maybe it's better to do this on qp bar from the start. All right. So now I give immediately the main results about all this. So basically, this is the result allowing you to do p-adic integration. So there is a unique way to associate every x over qp as there here. So as above, and omega here. Rational form on x here, f omega, and I will not explain where it lives. At least I'll say it's locally analytic. I will need more theory to explain exactly where it lives, but think of it as a locally analytic function on x minus the poles of omega. Here, f omega define up to constant, because of course, if I take a primitive, I add a constant, well, it's still a primitive. Okay, so everything I will say afterwards makes sense up to constant, additive constant. Such that well, at least 1, 2, 3 conditions are a bit obvious. So what do you want to be? Let's see. What do you want it first to satisfy? Yeah, you want this to make sense. So for locally analytic functions, I can make sense of differential. I look locally what happens, and this defines a differential. So you want this to be true, of course. You want a primitive. Okay. So second, you want some sort of consistency of the choices of primitives, and I said it's not obvious in general. So what happens if you want a primitive omega plus omega prime? Yeah. So you want the rule to be linear. Okay. So if you think about it, you go inside the space of locally analytic functions on open sets modulo constants. Okay, to make sense of the expression. So omega here, f omega is linear. Of course, when you have fixed x here. Fixed x, you take 2 omegas here, the sum gives you sum. Just to have some consistency. Now, there is a clear choice to be made when f omega. So if omega is equal to df with f inside this space here, and this is why I defined it before. What do you think is the choice of f omega should be? Here, when we already have what we wanted, let's keep it, right? When in this space we already have a primitive, we're good. This will be the right primitive. And finally, a condition of consistency when I change the variety. Here, if we have phi from x prime to x with x prime to qp also smooth and geometrically integral. Okay, so same thing for x prime. Well, I can pull back the forms and I can pull back the primitives. Okay, and I want them to be the same. So I want the primitive of f star omega, of phi star omega, to be. This should be something living as a function in x prime. Okay, and I know how to do this. I take the primitive of omega composed with phi. Also, could also be called f phi star f omega. Okay, maybe to mention name. For periodic integrations, there are 2 names to mention. The first one I already said, it's Coleman, developed a lot of the theory, but he did not develop it this way at first. So this version is more due to Kolmez. So we interpreted it afterwards. All right. Well, it's a bit axiomatic, but then it will work fine. Oh, sorry, I should have said here. I forgot the important thing. Good thing you have a big chart. Here, I can only primitive closed forms. Okay, so all this makes sense only for closed forms. Why is that? Because, well, if I can write a form like this, if I apply d twice, automatically 0. So, because the differential operator works this way, so of course the initial form has to be closed. Okay, but if you remember, it will not be a problem for us over abelian varieties because they're all closed. At least when they're global. So this should be easy. And then for any points PQ in X of QP, we define the integral of PQ omega by F Q minus F omega of P. Okay, it makes sense because, well, the constants cancel each other if I change the constant. So this is well defined. It's the usual formula for integration, actually, if you think about it. And I should say again, we have primitives locally. If you're on a disk, if you can expand in power series, if you know this is closed, well, you can find a primitive pretty easily by manipulating coefficients, and you will have a primitive. Okay, but the difficult thing is to have a nice choice for everything at the same time. And here I should also mention, and this is more obvious with Kalman's theory, but there is one last thing which is good for us, is that if XP has a smooth model X over ZP, say, here, okay, when I have a smooth model, I can talk about residue disk or residue polydisks, as I explained yesterday. Okay, so I have natural candidates for the local analytic open subsets. And now F omega is analytic on each residue disk. Okay, it means it has to be a power series on these disks. So then I can really calculate with the expansion of omega what should be the primitive. I don't have any choice in the matter in this case, right? Just for consistency. And I will explain very soon what it means for curves. And you'll see it ends up being very simple. All right. Do you have any questions about this? All good? Bit of a theory, but you'll see once we have this, it's very convenient to use. Okay, now, if you think about it, if I look at a point on an abelian variety, I want to give it some sort of value with a form. I can do two things, actually. I can integrate the form here from 0 to the point. I can also use the logarithm, which is here. So I can use the logarithm and get inside the tangent space. And this is exactly the dual space or the cotangent space at 0, right? And I said here that I can relate it to the global forms this way. So I can evaluate the form at the tangent space at the points given by the log. So actually I have two different things going on to rate one forms with points. All right. Well, the good news is it's the same. That's one of the main things as well. Here, I take an abelian variety, and then all P inside A of QP, all omega inside the global forms. Here, if I integrate omega from 0 to P, it's the same thing as evaluating the form restricted to 0 on the logarithm of P. So this belongs to tangent space. This belongs to the dual tangent space. Okay, so I could say at least that in the case of abelian varieties, I already know what should be integration. And actually, well, if you want to dive into the theory, you can, but that's, I guess, might have been one of the intuitions of Kolmez. He built the existence of this by going through abelian varieties and figuring out on abelian varieties it should work in a very specific way, and then pull back on all other X possible. So it sort of makes sense as well. Again, I will not give a proof, but for those of you who like periodic theory, it's actually quite fun. If you fix omega, for example, oh sorry, if you fix p and you look at the function in omega, right? Can I think of it this way? But if you want a small, what you really want to say is this: p associates omega associates the integral. Okay, so this takes a point in A of QP and sends you a form to the integral. Okay, and you can see a form global as a form at 0. So actually, this does go to so from A of QP to the tangent space here. All right, because tangent space is a dual of the cotangent space again. And so it has the same space of beginning and arrival as the logarithm. It's also additive, you can check. And it's additive, if you redo the proof, it's additive because the forms are invariant by translation. Or it should be clear also with this, that the formula for change of variables, because of this, when you change variables, it's really what you imagine for integration. Okay. I should write that. Let's say integral PQ of phi star omega is equal of P phi Q of omega. This works. Okay, because of this. Okay, so you have something additive, analytic, locally. And now you can check the derivative, the differential at 0. And the differential at 0, if you think a bit about it, it's exactly the identity. It's meant for it, because you end up with the primitive of omega. So you start with the primitive, you get back to omega. So differential at 0 is the identity. Okay. And now if you can use some periodic theory, this makes it necessarily the unique possible logarithm map on A. Like it's more classical. Again, references in the notes. It's not too difficult. The tangent space is canonically dual to the cotangent space. Okay, so here actually I should say it's omega. Here it's omega. It's considered as a form on just on the cotangent space at 0, but I can extend it by this to an actual global form. Okay, so I start with the cotangent space at 0, go back to global form and integrate. Okay, so I don't do a choice. Yeah. Yeah, I'm putting function. It's sorry. Maybe you cannot see from here. To omega, I associate the integral. So it's a function on omega on omegas. Yeah. It's perfectly canonical. This is canonical. Yeah. Not exactly. I've written what I could in the notes. Yeah, this, if you have, first you have a good integral model only if the abelian variety has good reduction at P, okay? And if it does, you can see this, you look at this set of points reducing to 0 mod P. And this one is very good. The set of points reducing to 0 mod P, it really looks like ZP power D. And it reduces to, inside the tangent space, it reduces to the set of points reducing to 0 in the tangent space over ZP, all right? So to be clear, we know what happens for a slightly smaller space. Here we have something that's really like ZP power D, reducing something really like P ZP power D. But above that, it's not very clear. You have a finite thing above it. It's not very obvious what happens, but almost. And yeah, and in this case, the group A of QP is 0, so the set of points reducing to 0 mod P is what is called a standard periodic group. It really looks like ZP power G, and the group law is given by a formal power series. Okay, where was I? Almost good. Oh yeah, and now what I want to do is integrate one form explicitly with this because, well, now it's all well and good, but I don't have a formula. Naturally. But if you understand, it's not really important to have a global general formula. It's more important to know it exists. And you know you can compute it locally, and I will show you how. Locally, it will not be too difficult. Because we have done all the work to make it quite obvious. So, yeah, that is something that will appear in the different aspects in the talks, I think. So for me, clearly, for Jan probably, for Professor Gatte is the same. It's a Q expansion, okay? Of course, I'm not talking about modular curves here, but I need to expand modular form, what will be used for modular forms in my case, and for me, it's one forms. I need to expand this in power series, okay? I explained how to do it for functions yesterday, and now it's actually pretty clear to do it for forms in this way. So let's start back with my good old curve of a Q and look at the p-adic points. Okay, so I can start with the global C, let's go with CQP here. The global one forms. Well, in particular, I can restrict them to any space inside CQP, and I'm interested in here what happens around the point P. Okay, so I can just reduce them to omega 1 of the local ring at P. Okay, just here over QP. Well, this is not very easily described, so I'll do the same as I've done yesterday. I'll go to the completed ring. So I tensor with OCQP P over QP at here. And this turns out to be the same thing as omega 1 of the completed ring. And why is it good? Well, now I know what to do. Because this, if you remember, it's basically a ring of power series if I have a uniformizer. So let's take SP, a good uniformizer at P here. This will be exactly QP of SP DSP. Okay, by construction of the Keller differentials, you can check it very easily. So now I know to one form omega here, I can associate an expansion which will be of the shape sum for n from 0 to plus infinity of an sp power n dsp. This belonging to QP. Okay. And by abuse of notation, we will often write omega is equal to this. Okay. But I know how to expand the form locally into a power series. And if you've understood or followed what I've done just earlier and yesterday, all this fits nicely even with an integral structure. In other words, if omega is integral normalized, okay, so it's not only a form here, but makes sense over the integral model. It means that all this can be extended to the integral situation. And in turn, instead of QP SP here, I will have ZP SP. In other words, these coefficients are not only in QP, but in ZP, which is why it was important to write it and be careful. Each in AN is in ZP because it's integral. And because it's normalized, I can also say that one of them is non-zero and modulo P. And one of them is not in PZP. So we're really setting ourselves for the easiest case possible of the Newton polygons things. Okay, just have integral coefficients, we'll integrate this, it'll be fine. Because now the omega bar makes sense inside C omega, and I can write omega bar by the same way as sum of AN bar, SP bar, and the SP bar. So this lives in FP. This is a uniformizer at P bar by construction here. And so this is an expansion for the local ring at the reduction of P modulo P. This all makes sense, and you can really compute this way. All right. And now what is the integration? Well, as I said here, F omega has to be analytic on each residue disk. Okay. And here I'm looking at the analytic function, so a sum of powers of SP power n. Okay. I want to integrate something like this. I don't have a lot of choice. Up to constants, I'm sure I have to have sum of AN SP power n plus 1 divided by n plus 1. That's the only possible choice I have for a local primitive. So for all, right here. And that's the usual formula for all P. So for all Q inside the residue disk at P, okay? So this only makes sense when Q and P have the same reduction mod P. Should make it clear. Okay, the same residue disk here. I have the integral from P to Q of omega is equal to the sum n equals 0 plus infinity of AN SP of Q n plus 1 divided by n plus 1. All right. And maybe for sanity, we'll check that this actually is well defined. When Q is in the good residue disk of P bar, it means that the reduction of Q mod P is exactly this. So the uniformizer here has to be valued in PZP. Okay, so this belongs to PZP. By what I said before, evaluation, this belongs to ZP. And so this does converge nicely. Right? Oh yeah, sorry. Yeah, yeah. I guess it deserves a big board. This so for all Q reducing at the same point as P mod P. So in other words, Q is in dx if P bar is equal to X. Okay, in CFFP. The integral there is equal to this sum AN SP of Q n plus 1 divided by n plus 1 here. And now, as I said, maybe colors, this is in ZP and this is in PZP. It really is a converging power series here. And now I have to solve this. Well, I haven't yet found the equation, but we're close now to explain what the equation should be. All right, so see, that's what I've done all this before, that at the end we end up with a power series with nice coefficients and a known in just one variable. Okay, so as simple as possible. Right. So now I can explain the theorem of Chabauty and Coleman. So I should be clear, the original version is Chabauty 1941, as I said yesterday. Coleman's version is much later, 1985, and now you know why, because we need periodic integration to make it work. But it will give something much more explicit. So we assume that R, the rank of G of Q, is less than G, the genus of C. Then we have many things happening. There exists a normalized integral omega inside h naught of j omega 1 j q p omega 1 such that, well, omega restricted to 0 vanishes on the whole image of j of q by the log. Okay. So I'll maybe say a few words at every step because the proof now is almost obvious. Why is that? I start with something of rank R less than G. I apply something additive. So the image has to be still of rank at most G, at most R, sorry, at most R, okay? So it's still not enough to fill out the whole space here. So it means this can be isolated by a linear equation in the tangent space, okay? And linear equations in the tangent space means exactly an element of the cotangent space, omega 0, okay? So I can end up with a form in a cotangent space that vanishes here, which I can lift to a global form here because of what I said. And then I can scale it so that it's normalized integral, right? So it's actually pretty natural. And this is called the vanishing one form for obvious reasons. All right. Now, the consequences, I fix it, okay? I fix such an omega. For this omega, well, first, all P and Q in C of QP, the integral of omega from P to Q is equal to 0. And here I should say, I see it as a Fourn curve, C. Okay, I advise you to do it as an exercise to convince yourself. But this, how do I compute it? Omega C is the pullback of omega seen on J here. So it's integral of from P to Q to the pullback of omega J. So it's the integral of omega on J from iota of P to iota of Q. I can now make a difference because it's a translation invariant. So it's actually the integral of omega from 0 to the divisor Q minus P. And now Q minus P is rational, okay? So it's actually the same as looking, so this will be iota of P minus iota of Q minus iota of P. So I look at this integral, and this will be defined with the log J of Q minus P. But by hypothesis, this belongs to log of J of Q, and it's cancelled by omega 0. So now I have set up everything so that it works really immediately when you follow the equalities for the integral. So I have integral like this, and it's not really useful except when the P and Q land in the same residue disk. Because for now, well, I have to say it's not very obvious. For now, I have no sort of any formula except in this situation. Right? I don't know if any, maybe some people will know more than me about this. I think there might be some formulas to use when P and Q do not have the same induction on P, but it's not very clear. So now we use this. Okay, and we use this and we have information, yes. Oh yeah, sorry. Oh, yeah, sorry. Yeah. Of course, yeah. For C of a QP, it has a lot of different values. Thanks. Big typo. C of a Q, because I use the image of log of Q, log of J of Q here is 0. All right. Third point now. Well, I can apply what I said yesterday about the Newton polygons and solutions here. So everything is sort of determined by how soon this is non-zero mod P. Okay. So if you follow what I said before, and yeah, and what name does it have? What name does it have? How soon this is non-zero mod P? Well, it appears here. It's how soon this is non-zero, and how soon this is non-zero has a name. It's the order of omega bar at x. Okay, so I should write it here. Here it's because I chose a uniformizer. It's the order of omega bar at x. Okay. So now I can just say everything with this for all x in C of Fp. If the order of omega bar at x is n and less than p minus 2, here I know that the disk intersected with C of Q is of size less than n plus 1. Okay, so I have basically nothing to explain about this. It's just looking at the Newton polygons and the corollary I explained, which was precisely of this form, if you remember. Something of the shape an over n plus 1, t power n plus 1. So this is just a consequence of that. And now, putting together all possible bounds on this, I get if p larger than 2g, the order of C of Q is less than the order of Fp, of Fe points. I count Fe points, and I add 2g minus 2. Do you know why the 2g minus 2? Where does it come from? Yeah, Riemann, exactly. It's the sum of orders of omega bar at every possible point. It's 2g minus 2. I know about this. And p larger than 2g to guarantee that p minus 2 is larger than 2g minus 2. So that's, I do have this all the time here. So this is just applying Newton polygons and putting together all the bounds. And do I have something? Yeah. Say, yeah, for now. That's a bit more right afterwards. Okay, so I do get, in this case, a bound on the number of rational points. For now, it doesn't tell me at all how to find them completely, but bear with me for 10 minutes and I should be able to explain to you how we hope to find all of them. But at least it gives you a quite nice bound, and often it can be optimal. So we know cases where this is reached. I don't have any on the top of my head, but maybe I should put one of those in the notes just to convince you. But this is quite neat already. Okay, before I give some variations that I find very interesting, even if it's just me, do you have any questions? Oh, it's just the number of points the residue disk rational. Yeah. So it's just. Oh, I mean, what is this? It's inside the C of QP. So inside C of QP, I look at the points reducing mod P to X, and among them, I look at the rational points. Just I want to avoid writing the details. Oh, for now it's an if. Okay, I assume this. Okay, and why I assume this for P larger than 2G? It's because then P minus 2 is larger than 2G minus 2, and I know the total order of the omega bar is less than 2G minus 2. So if this is true, this is automatic for any x. So I can apply this. Again, I advise you to check. I think I've done most of the work now. I advise you to check if you want line to line this with everything I've said before. It should be quite natural to convince you, knock yourself out. But yes, it's also very interesting to see what we can try to improve. I think there are some techniques to improve in many places. Once you know this, you might want to try what are the good cases. Oh yeah, for number fields. What is the right hypothesis? Well, obviously the most natural one should be this, the rank of the k points less than g. Natural, but afterwards there is something a bit annoying. It's the behavior of this. You have more possible solutions because you have possibly more valuation. So it's a bit more, this is a bit more demanding to figure out. I don't remember exactly what, you can find bounds, but you have to find, I think, a larger P or something like this. Yeah, if you have a difference, if G minus R is large, you can slightly improve this as well. Yes, because you can sort of manipulate different forms. It's not easy to write actually to make sense of it, but yes, you can do a bit better. Oh, yeah, no, B is not really. I mean, for the actual computation, what you do is you have to start with a known rational point, because you need to compute things like this. So you cannot really do any computation, I guess, if you don't know already one rational point, and then you go with it. For the prime P, you can change primes, and I will talk about it at the end. Yes, because you have many, well, you have almost all primes are good, so it's good. Of course, the bound gets worse and worse when P grows. Yes. Yeah. This, it's, well, at least here it's at most 2G minus 2 all the time, but that's all you can say, yes. Otherwise, the order of reduction changes. Yes. Yeah, well, this already depends on P. I reduce a form on P, yeah. Yeah, and it's actually quite interesting. But yeah, maybe you were thinking about modular forms. Modular forms, basically, you can have information with the one forms here by looking at what are the divisors of the first coefficients. And then you know for every prime except the ones dividing this, you have n is equal to 0, so you're good. That's one way of seeing it. Oh, I have to admit, I've never thought about function fields for this context. Yeah. I'm not sure. I'm not sure what happens. Right. Other questions? Okay. So I'll present two variants of the method. The first being my favorite one of variants or extensions. First, if you've noticed, at this stage, I don't need the whole argument before anymore. If I find an omega, the rest applies. Okay. Now I don't care how I find it. If there is one, I'm good. So now, is there a way sometimes to find an omega, even though this is not true? Or a simpler omega? The answer is yes. The answer is yes. And I can provide one example. I assume that J is not simple as a variety. So I assume there is a surjection from J to A with A abelian variety over Q with rank 0. It's called the rank 0 quotient. And should mention it, not a trivial one, okay? It's really an abelian variety with dimension at least 1. Then, for all omega inside H0 A omega 1, QP omega 1, pi star omega A. So if I want to say just here, sorry, the pullback of omega A is automatically a vanishing 1,4. I don't have any more time to explain it, but it's a very small exercise. Try to integrate, or maybe try directly to integrate here and check what happens. It's 0 on integral here. Another reason would be that the logarithm sort of factors or is functorial when you go here. So basically, this form only sees what happens on A. And on A, you have no rational points to torsion, so the logarithm has to be 0. So I have found in this case, I notice I haven't said anything about the general rank. I don't know about the general rank, so it's not mandatory. In this case, I have automatically a bunch of vanishing 1 forms. All right? And even better, I can see something a bit geometric about this condition. I'll tell it now. Then for all x in C of FP, 4. So I should say that pi, so J has good reduction mod P, A then must have good reduction at P as well. So I can extend to neural models. And this allows me to talk about what happens over FP for this morphism. So I get a morphism in particular from JFP to AFP. Then if the tangent map of iota from C to J to A, so at X, CFP is non-zero. Okay, so that's what I will call a geometric argument. I just have to study what happens. So I send a curve inside the Jacobian and then I quotient. And I hope that this has somehow a non-zero derivative. So in other words, tangent map is non-zero because this is dimensional 1. Okay, so I have a tangent vector. In other words, if I imagine J like this, A like this, and the projection like this, I hope that the tangent vector is not vertical. Okay, I want it to be non-vertical. In this case, well, I have a lot of things happening. And the consequence is that here, the consequence is that if P is larger than 2, then X has at most 1 rational point above it. Okay? In other words, it's alone, any rational point is alone in its residue disk. As an exercise, if you have understood the proof and what happens if P is equal to 2, I can say it's at most 2 actually. Yeah. All right. Here, I will just sum up quickly the argument, which is not very difficult. First off, notice that this is not mandatory to have rank 0 quotients to have vanishing 1 form. If the rank of A is less than a dimension, I can find a vanishing 1 form omega for A of Q. And when I pull it back, it's a vanishing 1 form for J of Q. Okay, but why it's really useful to have 0 here? Because it means I can use any form I want as a vanishing form. And then the fact that there must be, I want to find an omega bar so that the order is 0. And finding a form so that the order is 0 among all forms here means basically finding a map, finding a form that does not vanish on a tangent vector image. And when I go from there to there, and I want to find a map, omega, locally, not vanishing here at the image, it really means that the tangent map is non-zero. Okay. So there is a really nice geometric argument here. In some cases, we hope to make it more precise. So that's one of the good cases where I can prove that the best thing I can prove, so that any point is alone, if possible, many points are alone in the residue disk. Okay, which is why I wanted to talk about this one. It also means something that will be very useful. I think I'll talk about it next week during my talk for the conference. But it also means in this case that I don't really need to care about what happens on J. If I have a good A, I'm fine. Which is often all that we can ask for a modular curve, for example. So it's a good to have something like this. Okay, now in the last, I think, 10 minutes, I will explain how, with this method, which doesn't seem very explicit or not really, how should I say? It doesn't look like it will help you to figure out all the rational points, except if you're very lucky and you have found enough points here to have equality here, right? This would be very lucky. It happens, but it's not common. So how do you do if you don't have everything? Well, you do something called the Mordell-Weil sieve, which I will explain right now. So I have tried to find a formulation that's sort of self-contained. It's always a bit involved, but you'll see it will be longer for me to write it than for you to understand it after I explain, because I need a bunch of notations. So let's go with a sieve. And that will be the final point of this talk. Okay, so, and this is actually what happens, what can be computed, okay? So you have to assume that everything I say here is hard-coded into a computer. There are equations, there are descriptions, you can manipulate it. So first, I assume for simplicity that J of Q is free. So I just want to avoid things about torsion points. So I'd say it's of this shape, okay? I have a bunch of elements, so I assume I know explicitly D1, dr generating J of Q. Okay, and I define a function, which again has at least, well, at least it's what explicit, a function phi from C of Q to ZR, it's injective, which to any rational point associates basically its coordinates here. So it will be the set of numbers n1 and r such that phi of Q is n1 d1 plus nr dr. Okay. The goal will be to say that the image of phi has to be small and very, very small, and to end up with so few possibilities that I already have all the solutions. Yes. Oh yeah. Yeah, thanks. I don't have Q. Yes, thanks. Yeah, the image of the point in the Jacobian has to be something like this. All right. I assume I have a set of rational points, C of Q known. Oh, by the way, I should maybe slightly change what I said. There are examples when we don't know any rational points, but we still manage with some sort of tricks. I will not enter details, but I have modular curves in mind. But let's say here we have a set here, E, which is known, explicit known, non-empty, a set of rational points. Okay. Set NP the order of the reduction of FE points. So again, I assume that I have good reduction at P. So I have it makes sense to reduce the Jacobian mod P and count its points. It's finite. All right. And the reduction mod NP would be from ZR to Z over NPZ or what you imagine a reduced mod NP for each coordinate. Okay. Now the basic argument, if you reduce, you can reduce points from J of Q to J of FP, okay? And what you can at least say is that if you add NPD1 here, it will end up in 0 because the order is J of FP, all right? So you can identify points in J of FP at least by congruence classes in Z over NPZ R here. And this ends up being, so I can define points among those which I want to be isolated in residue disk. So P bar, P in, so P mod P. With P in E, and I know that D P bar here. So I want to look at points among those who I know by any possible means that they are alone in their residue disk mod P. For example, I have found omega bar of order 0 here, and P at least 3. Okay, it's not important to know how. What's important, is I know some of those points. Now, what is the conclusion? And it might be completely unsatisfying as such. I will explain more a bit afterwards. What's happened now, as a very basic exercise, I'll let you just run the inclusions. If I look at the image by phi of any point which is not in E here, it has to be included in the Z power R minus the inverse image by the reduction modulo NP of the reduction modulo NP of points of EP. Okay, which is translating two things. In fact, when I reduce from here to here, I can factor by Z over NPZ R, and the fact that these points have to be isolated in a residue disk, so you're not allowed to have any other rational points of C coming there. That's all. So you end up with this. You end up with saying that the rational points I don't know have excluded congruence classes modulo NP. Okay? So of course, as such, it's not enough at all to say that, okay, if you try with one prime, it will not tell you much, right? Just say, okay, I know I have some congruence classes, so why should I care? Well, what happens if you take multiple primes? The natural reaction, at least it was for me, was like, wait, yeah, okay, take another prime. The order might be coprime, and so I just have congruence conditions modulo multiples, right? So it doesn't, of course, it will have more and more conditions, but not enough to get finiteness, right? Well, actually, what happens is that the orders NPs, when P changes, are not coprime at all. That's just a phenomenon. And because they're not coprime, if you think about what happens for the Chinese remainder theorem with non-coprime elements, you have some incompatibilities of congruence classes, which excludes them. And it's exactly what happens here. When you take multiple different primes, you have congruence classes you have left, and some of them are incompatible. And if one of them becomes incompatible with all other possible cases mod Q, you take it out. And doing this with multiple primes, you exclude more and more cases. And if you have found C of Q large enough, at least you reasonably think you have no other rational points, it's what's been noticed for many examples. You end up by excluding all possible cases at the end. So you end up with knowing you have found all rational points. So that's why it's called a sieve, because you exclude things prime by prime. And it turns out that sometimes you can exclude more by incompatibility of congruences, which is a phenomenon I cannot really justify, just happens. And it seems to work pretty well. So at the end, you can, in practice, often compute this with actually a limited number of primes in general, I believe. Not too many. All right, so this concludes what I wanted to say about classical Chabauty. I said some things about p-adic integration, also because we'll do a much more advanced version of this in 2 days, which is needed for quadratic Chabauty. So sort of you recognize some of these tools, but be more involved. All right, thank you very much.
Any questions?
Oh, I'll find you one, but yeah, you need computers to work it out, of course, because you need many things, including computing the orders of points mod p, computing the generators of Jacobian, etc. Yes, I can find you an example. It's not necessary just for this. Optimal quotient is more in Mayes's theory. Yeah, I should say in several cases it's not completely needed. You might need sometimes, but often you just can avoid it. Yes. Yeah. Oh, I found it as a bit slightly easier as a first encounter with the p-adic integration, but I'll end up being compelled to use other aspects of p-adic integration that are more common in the last 2 talks. No, it's just for theory. It's just to set up the theory a bit more efficiently at first. Yeah, I didn't want to go too much through rigid analytic geometry, so or things like this. But yes.
Any more questions? Let's thank the speaker again.